Okay, so people can hear at the back, right? Okay. Okay, so what we are talking about is so random walk. That is okay. Any questions? No. Okay, and so what we so we had a lattice and you start from some point and then you randomly move this way or this way, and then we say that at after n steps you can be at various places. So there is some probability distribution p probability that you will be at some, so this is origin and this is site x, probability you will be at xn, and this we calculated is some binomial distribution. And from this you can calculate like moments. So x average is x, and x square is so of course from the distribution you can calculate these moments, but we saw earlier that it's much simpler to just directly compute these moments. And the main interesting point was, so we just said that if you just write it like this, sum of some n random numbers and then it's easy to show that xn square is exactly equal to n. And then we can imagine that there is some lattice size, and we call that x square. So x square is just n a square clearly. So n a square, and then if you just divide this by some tau and multiply by tau, and tau is like the time it takes for us to take each step, then this a square by tau into 2, I put a 2 here, a 2 here, and this factor we just call it the diffusion constant, and n times tau is the time. So that is 2 dt, right. Okay. So I mean a square by 2 tau is so that is the diffusion constant, and so what is a is basically the mean square mean square displacement in each step, right. So that I mean Sanjeev showed that in general this is like delta x square average. So this is like in each step what is the average mean square displacement, and divide by the microscopic time. So he called it delta t, right. So this is the sort of diffusion constant. Okay, and then Sanjeev also showed that this diffusion constant actually also occurs in this equation, the diffusion equation. Okay, so I said that we can go from this probability which is defined on this discrete lattice to a probability density, right, which is defined as the probability that it's between x to x plus dx, and this satisfies a, so Sanjeev showed that this quantity satisfies a diffusion equation. Okay, so right, so these are kind of the important results on diffusion. Okay, so and the other thing that also Sanjeev showed is that if you are looking at a colloidal particle in a fluid, then you can either look at the probability distribution of a single colloidal particle and see how, so that is like you start a colloidal particle from the origin, after time t you see where it is, then repeat this experiment like large number of times, then you can find a probability distribution. Or you could just start a large number of colloidal particles from a one point and see what is the density, and both the density and the probability distribution will satisfy this equation, right. And if it is a colloidal particles, then also this diffusion constant is given by this Einstein formula or a Sutherland-Einstein formula. Right, okay. And so what you should remember is that if you are just looking at any diffusion constant, you should not use this formula. And so that's there was some question about what is Brownian motion versus diffusion. I mean, so that at some level is just definition, but what you should remember is that when you use this, you have to know under what circumstances it's valid, right. So it's valid only for a like a colloidal particle inside a fluid. It's not valid if you look at a dust particle in this room where the microscopic mechanism is quite different. Okay. Okay, so you should actually calculate if you take I mean if you take this what is this called deodorant in typical size of some deodorant in this in a spray, and if you calculate use this formula, you should calculate this number and just verify that the time it takes for the spray to go from here to there is actually really large. Okay, so it can't, this formula can't be right for deodorant. Okay. So therefore deodorant we would call, we wouldn't call it Brownian motion, though it's diffusion, right. So you should just, but it's at some level is just definition, and but what is important is that when do you apply this formula? Huh?
So is the eta very small there?
No, it's not. Huh? Okay, so okay, so there are a number of reasons this formula could go wrong. Like, okay, so for example, this formula, this. Okay, so this is also not always true. Okay, so there are some regimes where it's true. Okay, this is one reason. The other reason is that this, when you derive Brownian motion, you neglect, you assume that there are no like convection and so on. But in this room, that's the most important thing that's driving the particles actually. Okay, so it's really convective driven. The convection is of course still turbulent, which is why it's diffusing, but it's mostly convection. It's, so it's a different mechanism. But finally, it gives rise to diffusion.
In that case, it becomes space dependent.
Which one? Diffusion constant in this room, I mean, okay, it might be because there it's hotter and here it's a bit cooler. It might depend on that way. It might depend. But if it's a uniform room, it will be on some scale, it will be independent of position. Okay, so okay, so the next thing Sanjeev actually derived this equation in some way by looking at a model where each step is chosen from some distribution, right, phi of delta x. Okay, so each step delta x is chosen from some distribution. Okay, so let's see if we can write something like that equation for our discrete model. Okay, so we can also write a sort of actual diffusion equation just for this discrete model. Okay, so in our case, instead of p of xt, we have this probability function. So how does this evolve with time, which is this discrete time n? Okay, so we can write a discrete version of this equation. So and so let's just look at that equation. So okay, so both time and space are discrete. Okay, so now question is, how is p of x at what is so if I know the probability distribution at time, so there is this lattice, and at each point at some time n there is a probability distribution, right. So so there is some probability here, some probability here, and so on. Now at n plus 1, what is the probability distribution? Okay, so this is simple because the probability at here changes because things are jumping from here and jumping from here, right. So I just have to see what is the probability here and here at the previous time step, and multiply by the jumping probability, and that gives me the probability at time n plus 1, right. So probability at x is equal to, so I'll just do the unbiased random walk. So it's the probability that at time x plus 1 at the previous time step times the probability that I'll jump to x plus probability that I am at x minus 1 at n times half. Okay, so maybe we'll just make it a bit more general, and so let's give also so let's say the probability I go this way is p by 2, and the probability I go is p by 2 that way, and the probability I stay is 1 minus p. Okay, so 1 probability p by 2. Total probability has to be 1, right? Okay, so then this will change a bit. So this becomes p, and and then I also have a probability that it was at this site only, and I didn't move, right? So that's the probability I don't move is is this clear? Okay, so okay, so now what can we do with this equation? So first I will show that from this equation you can actually derive this equation if you go to the sort of continuum limit, and so that is so simple, so that's straightforward. So you should notice that this is actually exactly the equation that Sanjeev had written for the evaluation of like he had written it in continuous time, right, and some equation like this p of okay, so I mean this equation is just the like discrete version of this equation. So they are at the same level. Now we'll see how to go from this to this. So that is you just have to kind of discretize this go to the continuum version of this equation. So we just subtract and so this thing goes here, and you are left with p right. Okay, so now what I will do is so this is time. So now I will just change variables and call x times a as x, and n times okay, and so now if I and this okay, so so I just divide by let's say okay, so first I just divide by a, then I will get a small p, and then I divide by okay, so if I divide, because this is everywhere linear in p, if I divide by a, then I automatically get p, right. So I can just put it p, okay, and then I divide by time tau. So there is a 1 by tau, and here I put a square and I put a square here, right. Okay, so now you see that this is basically like p of and here I have this so this whole thing is now I'll just let me just call it d, right. So this is of course I mean, so this is p of x t plus delta t. Okay, so therefore it's clear that this is like del p del t. and is equal to d, and this is just the like if you, this is just the Laplacian, right. So this is just del 2p by del x square. Okay. Okay. So does anyone have a problem with like when I wrote this px, and is this okay? Huh? Okay. So earlier we learned that it should be 2a, but actually in this case you don't need a 2a. Okay. So can someone say why you don't need a 2a? Right, yeah, because there is a weighting probability. So in this case you don't need a TA. So if in this case if you do if you actually evaluate the probabilities, you will find that it's non-zero at all sites. Okay, there is no site where it's 0. Okay, so if you do a simulation and you have a waiting time, then if you really want to go to the continuum limit, you don't have to divide by this 2a, you just divide by a, and you get the correct answer. Okay. So okay, so in this case, so this is what you so this is another way to derive this diffusion equation.
But what happens to the limit p going to 1?
Oh right, yeah. So now the diffusion constant is basically a square by 2 tau, which was the usual diffusion times p, right. P is something which is less than 1. Equal to 1, you get back the old thing because you don't have a waiting time. Oh, you are saying what happens to that thing? Okay, I mean, so things just work out fine. Okay, you can imagine there's a fine. Yeah, see, finally, actually, what I should really be doing is I should divide by dx, which has many sites. Okay, I mean, in this case, even a one site will work. Okay, so but the final result is of course so same, whether I take 2a or start with what. So the final result doesn't matter. Okay, but I mean this is the basic argument. Okay, so so basically if you have waiting time, then the diffusion constant is slightly smaller. I mean it goes down by factor p. Okay, so the so one thing that's really useful about doing this, and then we saw that this equation actually you can solve very easily, right? Just do Fourier transforms and you get this Gaussian solution, right? So solution is T. Okay, so of course we I mean this earlier we derived this in a completely different way. We did some combinatorics and found this object, right? You just counted how many ways you can go and so on, and we found this, and then we took some limits, Stirling's approximation, and we found this, right? So that was kind of quite difficult, but this way it's really simple. Okay, so the really good thing about this approach is that if you want to do it in, for example, 2 dimensions or 3 dimensions, on the lattice it becomes much harder, right? So how will you do? I mean, if you want this object on the lattice, that is obviously much harder. Okay, so so why is it harder? I mean, so let's just try to do it. Let us let's say square lattice. Right, and you want to do the same business, like now you say that at each time you can go in north, south, east, west with equal probability, right. So there are 4 ways you can go. Okay, and then again you want to take n steps, and if you take n steps you might so after some number of steps you might okay, you might have an object like this. Okay, and so this is 1, 2, 3, 4, 5, 6, 7, and you started from the origin 0, 0, and you ended up at some point which is -1, -2, right. So here the question is now if you take n steps, what is the you start from x bar equal to x1 0 0, and you want to know after n steps what's the probability you are at x bar, you are at some point like this, right. So if you take n steps, you can land up at various places around this point. I mean, again, there's some maximum place you can go. Okay, and you want to find what is the probability of being at various sites, right. So now, how will you, if you wanted to do this combinatorial way, I mean, how would you do it? So, so what would you do? The same kind of thing, huh? Right, yeah. So you have to just count the number of up steps, down steps, left steps, and right steps, right. So let's say L is number of left steps, R and up and down, right. So then what we know is L plus R plus U plus D is equal to N, right. Total number of steps must be N, and then what we know is what else do we know? Right, horizontal and vertical distance, right. So horizontal distance right minus left, that must be x1, and the other up minus down must be x2, right. So these are the number of left steps, number of right steps, number of u steps, number of down steps, and total number of steps is n. If I take so many right steps and so many left steps, I must be at my x coordinate must be this, and this must be my y coordinate. Okay, so now you see the problem. I mean, there are 1, 2, 3, 4 unknowns and only 3 given things, right. I mean, you have 3 equations, so you can't determine all of them. Like previously we could determine left and right uniquely, right. Given n and x, we could determine L and R uniquely. Now you can't do it, and so okay, so you have to sum over various possibilities. Okay, so here you can write an answer, of course. So I mean, in this case, so what is the answer? So first question is like, how many ways can you choose this LRU to? So that's okay. Let me write it here. So the number of ways of choosing is basically n factorial and then the probability of each guy is, of course, 1 by 4, right. 4 to the power n, probability of each configuration. And now I mean, so you can express R U D in terms of, so using these 3 equations, I can write R in terms of, let's say, n x1, x2, and left. Similarly, U I can write. So everything I can express in terms of the number of left steps, right. So this left step is still a variable, so I have to sum over all possible left steps. Okay, so this, I mean, is kind of complicated, clearly, right. I mean, to get an explicit answer in terms of x1 and x2 is difficult. Okay, so somehow in 2 dimensions actually you can still do this, okay, and you can get a nice exact answer. But if you go to 3 dimensions, you can't do it, and in general you can't, like, you don't have any nice closed expression. Okay, so on the other hand, this stuff we can still do. Okay, so I mean, you still have the diffusion equation in any dimension. No, it's like you have, it's in 2D also, it's not clear how to do it, right, but somehow you can do it. You have to do that sum. It's a complicated sum, right, and with some all these constraints. So it's a complicated which you can do somehow. But in higher dimensions, I mean, okay, it might be possible by some clever trick to do it, but generally you can't, I mean, you don't find closed simple expression like the 1D case. More variables, right, yeah, more variables, right, yeah. So it's, in general you can't do it, right, yeah. Okay, but so but now you can still do this continuum business, right, and you can get an answer for this probability density of finding x bar 2t. Okay, and okay, you still get the diffusion equation. Okay, so this will do later. You still P still gets is the diffusion equation, so the solution is still some Gaussian in higher dimension. Okay, so the final answer is always very simple for this probability distribution. Even though this combinatorial method does not work, but this continuum approach will, it does not give you the exact answer, but for many purposes it is good enough.
In 1D, you solve by this discrete method, and then you also solve by the continuum method. The answers agree exactly, in spite of the Stirling approximation that you have done in discrete.
No, I mean which one you said, the this answer. This answer I can solve by solving this equation and from the using Stirling's approximation, and this are exactly, they match exactly, right? Yeah, yeah.
In spite of the fact that we have used
Right, yeah, because it's for large n and all, right?
large n, it looks more like continuum.
Large n and continuum both are important, right? Yeah. So if you finally plot the, I mean the distribution, see it's I mean when is this accurate? Okay, so actually it's I mean, so first we know that x square, or let's say x square is like it goes as n, right? So if you look at the distribution of x, okay, supposing you plot the exact distribution, okay, so most of the distribution is actually concentrated in a length scale root n. Okay, so within this, after that it rapidly becomes very small. Okay, so the difference between this one and the discrete actually arrives somewhere here. Okay, so I mean there, yeah, like see, for example, this formula says that up to infinity it's finite, right? But of course you know that it can't go beyond n, right? So after that is obviously this thing is wrong, but I mean you don't care about those because it's so improbable. I mean you really don't care about the probability density there. Okay, so now let me, so in some cases, I mean you might actually be interested in solving the discrete equation. Okay, so how do you solve this discrete, so instead of a differential equation, it's called a difference equation. So how do you solve, so next what I will discuss is two things. One is another case which is kind of important in many real applications, is the case where you keep the space discrete but make time continuous. Okay, so for example, I mean there are all these things like what do you call molecular motors and stuff, right? So they typically oh, I don't know if they move on a lattice. Okay, they move in steps, discrete steps, right? But they move as like there is some rate at which they, it's not a probability, it's with the rates they move at so time is continuous and they are moving with some rate, okay, but it's on a discrete lattice. Okay, so there are many cases where you will have to study processes which occur on a discrete space but time is continuous. Okay, so let's just see how to arrive at those in that from this, starting from this, how to understand that sort of equations, and then we'll try to see how to solve both all these three different cases. Okay, so there are okay, so what I am saying is like you can look at so random walk, you can look at it either in like discrete space and or you can do time, which is basically what that description is, right? Both time and space are continuous, and this one both here. Another sort of useful system is the case where space is discrete but time is continuous. Okay. Time. Okay, and of course you can also look at continuous space and discrete time, but I won't write it. Discrete, everything discrete, and you have 1 with probability p by 2 and minus 1 with probability p by 2 and 0 with probability 1 minus p. Okay, and let's see, so we saw how to go from this to this to this, and right, we so now let's see how to go from between these two descriptions. So so basically we start with our this master equation. So P of x okay. So and now we say that each step takes some time tau, right? Okay, so we want to obviously to, if time is continuous, we want to have del p this side, but we don't want to put del 2p. So x is still discrete. We just want to turn this into a differential equation, okay, in time. So we subtract by p of x n. So minus p of x n, and then divide by tau. So put a okay. So then this basically goes to del. So I'll just still call it del p. Um, Okay, and this object p by 2 tau, it's a rate, right, 1 by time. So this is a probability divided by time, so that's just a rate. So this we'll call rate. Okay, and so basically what this equation tells you is that so I have this discrete lattice, and so supposing I am at some point x, then so there is a rate of so there is a rate at which you gain probability at this side because of things coming in with some rate r. Okay, so there are two gain terms, r times this, and then there is a loss term. So because things are going out at some rate, right? So so this is just this is a typical rate equation. Okay, so I mean quite often you will just write this kind of rate equations where time is continuous, and if you really want to like relate it to a discrete problem, you should introduce a probability p and time scale tau, and then finally of course when you go to this you have to take tau going to 0 limit, right? So you also need the limit p going to 0. Okay, so if you really want to understand do this mapping, you have to take the limit tau going to 0, p going to 0, keeping this ratio constant. Okay. No, if you choose rates, then right. So that's what I said. So if you choose rates in your simulation, time is of course discrete, right? So you just and you always jump with some probability, right? Not rates, because in your simulation you always have to use probabilities. You just say that with probability p something happens, with probability p, right? So you use a p, right? And if you want to connect this p to your whatever rate, then you have to do this identification that p by 2 tau is equal to rate r, whatever rate is there in the continuous time description. Okay, and you have to also actually take the, if you really want a good matching of results between the discrete and the continuous version, you need to take this limits p going to 0, tau going to 0 with this constant. Okay. So therefore, if you really so see in this case it is really important to introduce this waiting time, right? Otherwise actually you couldn't, because p equal to 1 is the case where you do not have a waiting time, right? So from that model you couldn't have got this continuous time version. Okay. So this one, oh here, plus is it? Okay, right, yeah, plus. Right, yeah. Okay, so yeah, so you to make this connection you need to have a waiting time, and the waiting time sorry, not the waiting time. So the waiting time is actually so p going to 0 means you actually with a very high probability you are waiting. Okay, so with a very small rate you are actually going out. Okay, with equal probability, and so this is the correct limit. Huh?
Are you not changing the velocity in some way, like
Uh,
let's say in a very small time tau, let's say hops.
yeah.
So then it's like, so earlier when you started the model in discrete system, so to hop it would take time tau, which
Uh,
was large. Like
Right.
there was
Yeah.
some kind
No,
of
tau was always small. The hopping so even there I said a square by 2 tau. You have to take a going to 0, tau going to 0, keeping this finite.
Yes, exactly. Yeah. So that you are taking a going to 0. So that means you are not.
A. So right now in this model, the a is just because I want to keep space discrete, right?
Yeah.
So that is finite. I mean whatever it is. I mean only changing time.
Yeah, but when you are changing the time, like it is hopping the same distance a when it hops, but in a much smaller time. So
It's hopping the same.
same distance a,
Yeah.
but
In this limit.
in much smaller time.
No, in this it's hopping in a, it's taking longer to hop, right? And the because I'm saying p going to 0, so p going to 0 means because this was the staying probability.
Yes,
So p going to 0 means I just stay
yes, exactly.
with a very small probability I go,
Yes, exactly.
right? Yeah.
But when you go at a very fast rate.
Ah, that I go instantly,
Yeah,
right? Yeah.
This is some kind of like you're taking this large velocity time.
Okay, I mean velocity. Okay, I don't.
If you think about it in that way, but there is no velocity.
There's no velocity, right? Yeah. It's you can think of it like moving with some constant. Yeah. Right. Yeah.
Yeah, so that is local process. Here it's non-local. We are talking about it probably doesn't matter.
Yes. So in this case, there's no I mean, when you move, you just move.
Yeah.
But you might move with any velocity is not right. Yeah, you can just it doesn't enter into the picture. Yeah. Okay, so now this equation. So how do you solve this equation? Okay, so for the first thing is that this equation you can also write it in this form, like say this p. Okay, so let me first just solve it in two different ways. Okay. So so basically we just follow the same thing. So when we had this so when we solved this equation, we said just do Fourier transforms, right? So here also you basically instead of Fourier transforms, you just do kind of Fourier series, okay, because it's a discrete lattice. So you just do kind of Fourier series, okay. So I mean, so the basically what you do is p of xt. Now you supposing I just define okay, theta x okay, so okay, so now x is discrete, so instead of doing a integral, I am just doing a summation over all x, and this is basically like a Fourier series, right? And I am defining this object which is like p of kt. So it's equivalent to p of kt for this process. Okay. Now if I do this, then the inverse is also easy to find. So p tilde theta t. So what is the inverse of this? T theta, so t of huh? Which one?
So, no, okay, so there it has Px on the, so either, so right,
Oh,
left
sorry,
hand
sorry,
side
wait,
should
wait,
be
wait.
P of x.
That's sorry, yeah. Okay, so this is just the inverse. So this is like Fourier transform in inverse, right? This is basically Fourier series, okay. And so that's how you solve this equation. I mean, I take this equation, and again in this case, I have to give my initial conditions. So initial condition is again p of x at time t equal to 0 is equal to, let's say, delta of x, right? Okay, so now I take this equation and I basically try to write an equation for p tilde theta t. Okay, so basically I will just take this equation, multiply this by e to the power I theta x and sum over x, right? That will give me an equation for p tilde of theta t, right? And so here if I just take e to the power I theta. Okay, so let me just write this step. So I have for this term I have something like e to the power I theta x and this is all x, right? So what I can do is I can just put a x plus 1 here and bring out a e to the power minus I theta, right? So this is basically e to the power minus I theta, and this is still p tilde of theta t, right? So so for each of these terms I will do something like this, and then the final equation that we'll get is so this is e minus I theta, and then this is minus 2 plus it is 1. Right. Okay, so this is basically equal to r. So this is minus 2. Okay, and you can see this is exactly like what Sanjeev wrote. I mean, this. Right. So this is, and so we'll now the solution of this is also the same as writing the solution of this. So we have p tilde of theta t is equal to what? So it's exactly this equation, right? Except dk square is replaced by this object. Okay, and so it's e to the power minus okay, so this is just okay, and p tilde theta 0 is what? Huh? Right, I basically use this, and so now p of x 0 I said was this, so it's basically what? So what is p tilde? Theta at time 0. Huh?
P of 0.
P of 0, which is, this is the initial condition, right? So it's 1, right? So this is just 1. So therefore the final solution is P of xt is equal to this object, so 1 by 2 pi sorry, there is a t here. So there is a t here. It is exponential. It's like previously we had e to the power minus d k square t. So here is just e to the power minus t something t at here. So t and then e to the power minus I theta x. Okay, so this is the final result P of xt, and this is actually if you do this integral can be done, it will give you some Bessel function. Okay, and this is some Bessel function representation. So you get some function which is known exactly. I mean, in some cases. So that's this is the exact solution of this problem. So again, if you take some appropriate limits again of like looking at x large and so on, then this will give you what? If you look at really large x and what? Gaussian, right? Yeah. So this also in some limit, if you look at this Bessel function and do some asymptotics, you will again get back the Gaussian distribution.
With the Gaussian, you basically
Expand, right? Yeah, actually, right. Yeah. So that's the other way. At you basically have to argue that at large time, large x, and so on. Like you look at x of order root t, that's important. You should look at x of order root t. Then this integral will get the most contribution from small theta, right? So then if you small theta, this is like theta square, right? Then it becomes a Gaussian integral, and you will get x square by 2 dt, right? So for large x, large time, you basically get back the Gaussian distribution, but in many cases you will actually need this like exact form. So here I wrote this equation del p to r, and then I have something which I will just call it's a Laplacian operator, right? A discrete Laplacian operator. So I will just define it as delta of p xt. Okay, so this is just the discrete Laplacian, and it's defined as so this object is basically p of x plus 1 t minus okay. So by definition this is equivalent to this. Okay. So now I mean if you think of this equation, it's basically you have some lattice and your space is discrete, so you have some so x equal to 0 1 2 like that. Okay, and you can think of this p as a it's basically like a vector, right? So this is so this is called a master equation, and you should think of this as a probability vector. So at each point you have a probability. So if you think of this just as a column vector, let's say p of x I mean all possible. Okay, so p x equal to so it's this of course an infinite vector. So but basically p of 0 t p of, so I can form a vector like this which I call p, right? It's just a probability a vector which gives me the probability at each site. Okay, so after some sites of course is 0, but I can just write this infinite vector, and this one is then basically and this is some another operator which in this case is has the form. So R delta, if you look at matrix, So it has the structure like this. Okay, so it's something which is one. Okay, so this object R delta, if so is basically a matrix like this. Okay, and this equation you can just write it as equation like del P del T equals to W P, right. So this is basically it's a master equation where W gives you, so your probability space is just the set of sites. I mean, so the system is described by just its position, and so I just need the probability at each position. Okay, and then this matrix gives me the transition probability between different sites. Okay, and in this case, because I can only jump to nearest neighbor, so this matrix is just off diagonal matrix. Okay, so I can jump either here or to nearest neighbor site. Okay, so this is the so this system is just described by this master equation. Okay, so now in general, how do you solve such equations? Okay, so just let's look at another example where we are looking at a same process but in a finite domain. Okay, so I mean you might just have Brownian motion within a box. So whatever we have been talking about is on the infinite line, right? And so you start with a set of particles, it keeps spreading, 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 and finally the probability everywhere is 0, right? But if you supposing have particles inside a box, then of course initially if you put some particles, eventually it will go to a constant density, right? So that is not described by the solution that we wrote so far. Right, so I mean so far what we did was we were solving this diffusion equation on the infinite line. So if you start with some density here, then it keeps spreading, spreading, and it goes to 0. But supposing we start, we have a box, right, and we start with some density here, then of course at long times it won't be a Gaussian, it will eventually go to a constant density, right. So therefore we have to have a different solution of whatever the way we solve this. The Fourier transform solution is not valid if we have a box, right. So let's do this on the discrete case, because it just shows you how in general also to not only solve this but also how to think of this discrete problem. Okay, so now basically if you have a finite system, so let's say you have a box of size so 1, 2. So you have 1 to L sites. Okay, so there are 1 to L sites, and initially you might start your you have a bunch of particles here with some rates. Okay, so there are some hopping rates. In this case, the hopping rates are all equal. So particle can hop with rate r this side, hop and with rate r this way. And you want to know what happen, how does the probability spread with time, right? Okay, so you know that finally what is the probability at each site? Finally the probability should just be 1 by L, right? So it starts from a delta function at this site, and at long times it's just 1 by L at all sites. So how do you solve this equation? Okay, so basically we still have this equation is still valid, right? But now this W is so P is first of all a finite vector. It just gives you the probability of finding at the particle at different sites. Okay, so if I have 4 sites, then this probability vector is given by something like P of 1 at time t, P of 2 at time t, P of and this W matrix is given by some matrix like basically if I look at this site, it can lose to this site, right, but it can only gain from one site. Okay, so there is a R here for gaining this site. So this is So here I can put a, so if I write in so if I write in component form, then I can just write this matrix equation in this form, right. So P is the Px is the xth component of this and this one gives transition from x prime to x, right. So if I write here W, so this matrix elements are so W, so this is W11, this is W12. So W12 is probability of rate of transition from 2 to 1. Okay, so this side to this side. So that is R, right. So this should be R. Then this one is W13. So that's rate of transition from 3 to 1, which is 0, right. So this is 0, and then 4 to 1 is also 0. So this is also 0. Then let's put this one W21. So 21 is the probability of rate of transition from 1 to 2. So this is R. Okay, let's put this later, and so this one is again R, and this is 0. So this is 0. This is R, and then this is. Okay, then we'll put the diagonal terms. So diagonal terms, this must be just minus R. This will be minus 2R. Okay, so and because things can't, so this can't go this way, so therefore this element is just minus R. Okay, so it can only lose to this side, right. So this is the rate of loss from the each side, and these are the gain terms. Okay, so this is I am just writing the random walk, but in a different language. Okay, so so this is the matrix, and now I have to basically solve this equation. So this this way I solved, which is using the Fourier series, that's valid only on the infinite line. Okay, but if I have to do it in a finite domain, then how do I do this problem? Okay, so the basically I have an equation like del P del T equal to WP, right? Okay, so now how do I solve this equation? Right, yeah. So basically find the eigenvalues, eigenvectors of W. Okay. So this, I mean, if you, I mean, this you already know, because it's basically like, I mean, it's almost like Schrodinger's equation, right? I mean, if you write. Okay, so if you want to solve this time dependent Schrodinger's equation, which is also a linear equation in psi, then what you do is typically you find the eigenstates, eigenvalues of H, and then you expand in those, put in the initial conditions, and that gives you a complete time evolution of whatever initial wave function you have, right. Now this equation is almost the same, and you have to do the same thing. So basically find the eigenvalues of W. So let's say I call them phi of n. Right, and then if these are the eigenfunctions, then any vector I can expand in this phi n's. Okay, so okay, so here there is one difference, is that this is always a Hermitian matrix, right, but W is not a Hermitian matrix. So which means it can have like all the eigenvalues may not be real, and left eigenvectors, right eigenvectors could be different, right. So that's important difference, but both are linear equations. Okay, so right now I am just looking at the right eigenvectors, and I can expand this guy as a n phi n. So I mean, so you should just think of right now this as some, like for this case it's just some row, I mean some column vector with 4 elements, right, and this is a 4 cross 4 matrix. This is in general it's a n cross n matrix, and these are n vectors. So the general solution is given by, I just sum up over all the eigen states, and if I plug in this equation, then I will get a solution for a n, right. So it's basically I will get a n dot equals to lambda n a n, and the solution is a n t and 0. Okay, so now this is therefore summation and now I have to find this a and 0, and I do the same thing. I use the what is the probability at time t equal to 0, right. So, at time t equal to 0, so this is at p of t. So, p of 0 is equal to summation a n 0 n, and how do I find this phi n 0, a n 0? Huh? What? Not inverse. I just take I multiply by a left eigenvector, right? Okay, so here, I mean, in quantum mechanics I would just have done like phi n star. Okay, but here I have to multiply by a left eigenvector, okay, which is not phi n star. So, so basically if I do that, this a n 0, okay, so this also has some left eigenvectors, okay, so I will just call them chi n, and the eigenvalues are the same, okay, and so what I get here is this is equal to sorry. Okay, so then my final solution is this object. Okay, so P of t is t, and then okay, so here let me just also write this. Okay. So I mean this is just notation, right? I mean I am just meaning a column vector. Okay. So this is the final solution, and this is exactly what you get in quantum mechanics. Okay. So if you have some initial wave function, this is how it evolves in time. Okay, and this is actually, if you think about what we are doing in the when we solved this equation, we are actually expanding in a basis of this object, right. When we expanded in e to the power I k x, these are just the wave functions of this operator, right. So that is what actually we are doing when we are doing Fourier series, but here you should not do a Fourier series, you should just use the eigenfunctions of whatever this operator you have in the with the boundary conditions and everything. Okay, so okay, so now therefore what you have to do is basically find this eigenfunctions of this matrix. So what are the eigenfunctions of this matrix? Eigenfunctions and eigenvalues. I mean this, I think all of you have seen, right, at least in solid state physics you get this matrix, right, and okay, in solid state typically you have something like, okay, you have oscillators and maybe they are on a ring, but this is like it's on the two ends are fixed, but and does anyone know how to find the eigenvalues of this? Huh? There is an equation. Okay, yeah, there is an equation which is the eigenvalue equation, right. So basically what is the eigenvalue equation? Eigenvalue equation is W phi, okay, I shouldn't write n here, n is a bit confusing. Okay, so this is the I am writing for the nth eigenvalue function. Okay, so let me just call it s, sth eigenfunction. So let us say W phi s equals to lambda s phi s. Okay, so now what does this equation really mean? If you look at this matrix, so phi s is a vector, right, with some components phi of, so the components are L. So L goes from 1 to 4 or whatever. So if you expand this equation, write the components, so then this equation is basically it's in general minus 2 r phi s L plus r phi of s L plus 1 plus r phi of s L minus 1 equal to lambda s L, right, and this is basically the same as this equation. Now we can you guess a solution of this? Huh? Okay, so one guess is let us say e to the power I q L. Okay, so phi of S L is e to the power I q L, okay, and if you put this in that, it will satisfy the equation, right, but it is not, you still do not know what is q. Okay, so how do you find q? Okay, I will give you another hint. I mean, if you look at this equation and if you look at the if you instead of L, if you took the continuous version, then this equation is what? E is basically d2 phi by del x square equals to lambda phi, right. This equation all of you have solved inside a box. Huh? Yeah, this is just particle in a box in quantum mechanics, right. So what is the solution? I mean, how do you find the eigenstates of this problem? Huh? What? Lambda is n square, but how do you find it? I mean, what is phi? Sine, right? Okay, so basically here, I mean, also it's sine. Okay, so here actually it's e to the IQL and e to the minus IQL, and then you have to take a combination such that it satisfies the boundary conditions, right. Now because the boundary is such that I mean, see you I mean basically you have to take this equation, but with the boundary condition that phi s at 0 is equal to 0 and phi s at L plus 1 is equal to 0, right, because you can just imagine that this whatever lattice you had, the endpoints 0 and L plus 1, there is nothing there, right. So you can't come from those sides. So you have to solve this equation with these boundary conditions, which is like solving a particle in a box with vanishing boundary conditions, right. In which case you in the continuum version you know sin qx, and actually in this case also the correct solution is so I will just write the solution, you should just verify all of this. So the correct solution is the normalized solution is 2 by Okay, so there are L different solutions labeled by this S, where this Q just varies. Okay, so it's exactly like particle in a box, except that now because it's a finite matrix, you have a finite number of eigenstates, right? Just 1 to L, and the eigenvalues are basically 2. So it's I guess 2. Okay, so these are the eigenvalues. So again it's basically like q square. In the if you look at small q, it's like q square, which is like the k square, but this is the discrete version, and q has so you have L eigenvalues. Okay, so there is some problem. I mean, there should be one. Okay, there should be one zero eigenvalue actually. How come there's no? How come there's no zero eigenvalue? Oh, 0 is there, right? Sorry, sir. Huh? No, there is a problem. Oh, sorry. This is a mistake. Huh? Yeah, so you need you need one of the, see right now if you look at the eigenvalues, if q is not 0, see right now the choice I have given q is not 0, right. So that means there is no 0 eigenvalue. So that means if so all of them are actually negative, right? Right, all of them are negative. Yes, no, so that's the problem. See, there is no eigenvector 1 1 1 in this problem. Oh, 1 1, right, yeah, 1 1 is an eigenvector, right. So that's not included in that. So that means I have done something wrong. Right, because right now I'm so okay. So what he's saying is that if I take this matrix W and put 1 1 1 1, that is an eigenvector. That is a no. That's no, even right one. Right. If I put 1 1 1 1 here, then this is 0. So there is an eigenvalue with 0. There is an eigenvector 1 1 1 which is eigenvalue 0, right?
Take the first first row.
Huh.
Then
It's 0, right? Minus r plus r is 0. This is zeros. I mean, so it's 0. Okay, so this is so there is definitely one 0 eigenvalue eigenvector with 0 eigenvalue, but out here I am not getting that, right? So therefore there is something wrong. Okay, so let's see what is wrong. Okay. Okay, so I guess I just put the boundary conditions wrong, right? Because yeah, because it should be sorry.
actually that is not
Right, this is not the correct yeah. So this is not the correct boundary condition. So this is this boundary condition that I am showing is something called an absorbing boundary condition. Okay, so this P of the probability distribution vanishes at the ends. Okay, which means that things get absorbed actually. Okay, so then eventually the whole probability distribution will decay to 0. Right, so because I mean I have written the solution. If all the eigenvalues are okay, so I think the sign was wrong, right? This is plus. So if all the eigenvalues are less than 0, then of course the whole thing will decay to 0, right? That happens if at the boundaries I have some absorbers. Okay, so things keep getting absorbed, so I lose probability. So but in the if I have a closed box which is described by this matrix, then I should have at long times the probability actually should be constant, right? Okay, so what is wrong is that so just let's look at the boundary conditions more carefully. Huh? Yeah, so the correct boundary condition is not the probability is not 0, but del p del x is 0, right? So in that case actually the solution is okay, so I said e to the iql, and then you can either take plus or minus I e to the minus iql, and you have either cos ql or sin ql, right? So if it's sin ql, then it's the probability vanishes at the ends. If it's cos ql, then the current vanishes at the ends. Okay, so the correct solution in this case is cos ql. And I guess maybe okay, so this is still true, and now q is L0 to okay, maybe I should look now. Okay, so this way to be careful. Okay, let's see if we can figure out in the next 10 minutes. If it's minus r phi of 1, phi of s1 plus phi of okay, and so now supposing I want to, and in other places, in most places the equation has this form. So it is minus 2r is R. Right, and in the last place it looks like basically right. So this is the set of equations satisfied by the wave function, and only the first and last equations are different from this. Okay. So now supposing I want to write this also in the same way. Okay. So what I can do is, supposing I just add a phi s0 term. So I'll just put phi r phi s0. Okay, and I also add a let's say I add minus r phi s1, right, this and I also add a okay, so I took this equation and I added and subtracted this term, and here also I added and subtracted this term, right. So now this equation also looks like this, but if I really as I have these two additional terms, and what I want is that this should be 0, right. So that's one. So that's the boundary condition, that phi s1 should be equal to phi s0. Does that make sense? Is that okay? It's not clear, is it? What I did here. So see, I had this equation, right? I mean, I didn't have this. I had this something like this. Okay. Now this equation looks different from this equation, right? I want to write this in the same form as this equation. So I add plus r and I write minus 2r, right? Then this one looks like this. And here also I had this term. So L minus 1 means 1 minus 1 0, right. So L and L minus 1 here. So here I put a r phi s 0. So I also subtract this. So now this of course is looks like this, but the extra terms that I have added, they must be 0. Okay. So that actually decides my boundary condition. Okay. So so the boundary condition basically is so earlier I was saying that it should be phi s0 is 0. So that's not the correct boundary condition. The correct boundary condition is phi s0 should be phi s1. Okay, and if you think of the again the continuous version, this is basically like del phi del x at the boundary is 0, right. So this is again like the current is 0 at the boundaries. So because this is a hard box and you can't have current going that. Okay. So so I just showed that this is the correct equation, and similarly at the other end you will find that basically you will get phi s at L plus 1. Okay, so so therefore you have to basically start with these two solutions. Let's say sin q L and try to make sure that these boundary conditions are satisfied, and that will determine this A and B and Q also. Okay, so if you put this one, okay, so let's now do this. Okay, so phi okay, so so the first thing gives A sin, okay, so A sin 0 is 0. So basically A sin q plus B cos 0, huh? P, and the other thing is okay, it's not simple. It's sin q L plus 1. A is yeah, A you can set to 1 because it will be like a normalization constant. So if you do that, then you can solve for B, and then you will get a equation which will determine the Q's, right. So okay, so it looks like it won't be simple, right. It's clear you will get some transcendental equation, and the roots of that will. So normally you just get something like e to the power, if it's periodic ring, you would have got something like EQ L equal to 1, and Q would have been just 2s pi by L plus 1, 2I pi s by L. Okay, but in this case the equation that you will get corresponding to this will be much more complicated, and you have to find the roots of that to find the Q's. Okay, so but the bottom line is that at least one eigenvector we have found, he found, and one eigenvalue which is kind of simple. Okay, so that's actually, you can also show that that's the only sort of eigenvector with all positive elements, and so one eigenvector which I will just call phi 0. So this is just this 1 1 1 1 1, and corresponding lambda 0 is equal to 0, right. So this will also come from solving this equation, but this we already know independently. Okay, so one eigenvector is very simple, and now what you see is that at very long times and all the other lambdas are all less than 0. Okay, so so what you find that at long times, I mean this will basically go to a okay, so go to this phi naught, and so this will so there won't be any time dependence, and you will just get phi 0 chi 0 p 0. Okay, so so chi 0 is also actually very simple. Okay, so what is chi 0 is just the left eigenvector. Okay, and the left eigenvector, actually what you can show is that there is one eigenvector which is just 1 1 1 1 1. Okay, so if you take any this sort of W matrix, so if you take any W matrix, so one property is that this sum of these columns is 0, right, because that's just conservation of probability, whatever. So it's there in the example we looked at, it was minus r and r. Okay, so sum of this is always 0. Okay, and that's always true for any this rate matrix. So one consequence of this is that if you write a vector like this 1 1 1 1 1, then that's always an eigenvector. Okay, so whatever these elements are, because if you do this product, I mean it's just sum of these elements, right, if it's all 1, so that is always 0. So you always have a left eigenvector with 0 eigenvalue. Okay, so so corresponding to so we also found a phi naught which is 1 1 1. That's a rare case, it's not, usually it's not constant, but in this case it's always 1 1 1, and if you normalize it, it's just 1 by L there, because there are L sites. So this phi 0 is 1 by L L, and chi 0 is this. So these are the left and right eigenvectors corresponding to this 0 eigenvalue, and then if you look at this, what happens here. Okay, so at long times, so t going to infinity, I mean basically you get p of t goes to this object, so phi 0 right. Okay, and now what is this? No, given chi0 we found, right, it is 1 1 1 1, and p0 is a vector which gives me the probability of at each site at t equal to 0. So, if I take this product, what is it? It is the sum of these guys, right, and that is 1, right. So, this is actually just 1. Okay, so therefore, the at long times it just goes to the this lowest eigenstate, which is just 1 by L, 1 by L, 1 by L. Okay. So, that is what we wanted, right. At long times it should go, it should just be a uniform density. Okay, so so this is like the ground state of the system if you want to think about it, and so at long times basically it's just goes to the ground state. Okay, so okay, so maybe you can just go over these arguments again today, like this I mean the solution of this discrete case and the way we find the eigenstates and so on. And if you have questions, you can discuss in maybe tomorrow's tutorial. Okay, so today's tutorial Sanjeev will take. Tomorrow's tutorial we can again discuss this. Okay, so basically what so let me just summarize what I did. Okay, so I started with this discrete random walk on a lattice, and where the system is infinite, and then we looked at how if I put a bunch of particles, how they evolve in time, and then we saw that you can how do you describe this in various cases where you want to either make space continuous and time continuous, and then finally we looked at okay, so some of the most important properties of this diffusion or Brownian motion is the way it's this wave packet spreads, right. So basically if you start with a set of particles here, then it spreads like a Gaussian in time, right, and this width is root 2 dt. So that's one of the most important things about this diffusion. And then we said this, okay, so we calculated this variance, and that's in general it's 2 dt. And so this thing you can calculate using various methods like combinatorial methods, and also by writing actually a time evolution equation for this object and solving that equation. Then we also saw how to write this in like a discrete space and with continuous time. And finally, we looked at the case where, so this solution is for the case where the lattice is infinite. Then we looked at the case where it's a finite box, in which case you expect something like you start with something like this, and then it's a finite box. So it should at long times go to a uniform density, right. So if you want to understand how this evolution takes place, you have to basically like solve the diffusion equation in a slightly different way. And we solve the diffusion equation for a lattice in a lattice model. I mean, of course, if you solve the continuous space, continuous time diffusion equation, that would have been actually much simpler. Okay, so that's maybe an exercise you can try to do. Okay, so okay, so if you have questions, please go through this today, and then tomorrow in tutorial you can ask and get everything clarified. And tomorrow I will give a set of problems which you can do over the weekend. So, so now I think there is a tea break, and then Aritra will show you this this Brownian motion. We have a microscope, and it's a digital microscope. Okay, so there is a screen, and if you put a slide, you can just see the pictures, and maybe he has also some videos he has taken which he can show of like not a okay, so one thing I today I didn't discuss is like motion of a bacteria. Okay, so if you look at a bacteria, it's not completely a random walk. Okay, so it's what it does, it's like it goes straight for some time and then randomly moves in some other direction and so on. So it's slightly different from the usual random walk that we discussed, and so maybe tomorrow I'll discuss how do you describe motion of a bacteria, again using similar language, but final results are slightly different. Some results are similar. Okay, so here some movies where something not a bacteria but some similar creature moves in some similar to a bacteria. Maybe he will show that, and I think Sanjeev will be there for the tutorial, right? Okay, so okay.